Hi everyone and welcome back to my YouTube channel. I'm Breck and today we're going to be talking about the acidification of the ocean. If you're new here, this is Be a Solution to Pollution, and I'm going to talk all about the different issues and things going on in the ocean, and as well as things that we can implement into our daily lives that help this issue and some of these issues. If you haven't seen my last videos, the first one is on ocean pollution and health, and the second one is on pollution in the fishing industry, like both sides of the argument. But this one is just going to be on acidification of the ocean and what that means and what we can do to help it. So first of all, what even is ocean acidification? So because of human-driven increased levels of carbon dioxide in the atmosphere, there is more CO2 dissolving into the ocean. The ocean's average pH level is now around 8.1, which is basic or alkaline. But as the ocean continues to absorb more CO2, the pH decreases and the ocean becomes more acidic. So why is ocean acidification? What is ocean acidification and why is it a problem? Ocean acidification is a global threat to the world's ocean, estuaries, and waterways. It is often called climate change's evil twin, and is projected to grow as carbon dioxide continues to be emitted into the atmosphere at record high levels. So what is acidification of ocean water? Ocean acidification refers to a reduction in the pH of the ocean over an extended period of time, caused primarily by the uptake of carbon dioxide, CO2, from the atmosphere. Next, what are the three causes of ocean acidification? There's actually more than three, but the biggest ones are raised carbon dioxide concentration in the ocean, raised carbon dioxide concentration in the atmosphere, and higher concentration of hydrogen ions in the water. So to start off with the first cause, raised carbon dioxide or carbon oxide concentration in the ocean. When the level of carbon dioxide gas gets higher in the ocean, it obviously affects the whole water. When sea organisms die on the seabeds, their remains pile up and form corals, which is consisting of carbons. Also, these organisms release calcium into the water. These compounds have a far-reaching detrimental impact on the composition of the water as they add acidity. Secondly, raised carbon oxide concentration in the atmosphere. Sometimes the harm induced in the atmosphere can spread into the waters. This is when carbon dioxide is released into the atmosphere through various human activities. This, in turn, contaminates the water because the carbon gases get to be dissolved in the seawaters, and this lowers the pH of the water, contributing to acidification. Third, higher concentration of hydrogen ions in the water. At the seabeds, there are some chemical reactions that may take place, and they can have negative impacts on the quality of the ocean water. Such reactions may include the increase in hydrogen ions, which when combined with other compounds such as nitrogen, water, among gases, and the reactions lead to ocean water acidity. Fourth, burning fossil fuels. This may not be directly linked to the contamination of the water, but it plays a crucial role in the changing of the environment. Fuels such as petroleum, diesel, and coal produce lots of carbon dioxide when burnt. This increases the concentration of carbon gases in the atmosphere, which in turn finds a way into the water. Carbon and other atmospheric gases find entry into the sea through acidic rainfalls or even direct dissolving into water. 5. Waste disposal. Disposals of waste has been a challenge to many countries. As for those that border seawater masses, they have been too quick on using the oceans as the possible dumping grounds of domestic and industrial wastes. Nonetheless, as the atmosphere shoulders the brunt of poisonous gases, seawaters are on the receiving end of dangerous liquid waste. Alongside direct sewage waste disposal, there are other wastes that increase the level of acidity in the water. As an example, industrial and agricultural wastes that have acidic compounds are very dangerous as they lower the pH of the ocean water. 6. Improper land management. Agriculture may also contribute to the problem of ocean acidity. It may happen especially when the methods that are employed by the farmers are not suitable. These are methods that may be prone to soil erosion, and in the process the chemicals are washed downstream into the ocean. In short, if the land is poorly managed, the water masses can be hit by the impact of acidifying soil mineral content and water pollution. 7th, industrialization. Countries or cities that have embraced industrialization pose dangerous implications for the environment. Their existence can only mean that there is decreased carbon dioxide concentration in the atmosphere, which when absorbed into the water, the level of this acidity increases. Industries contribute to the emission of dangerous gases such as carbon dioxide, sulfur dioxide, nitrogen oxide, and many others, which later form acid rain or dissolve into the oceans to create ocean conditions. So now, what are the effects of ocean acidification? First off, it increase in the carbon dioxide concentration in the ocean. Ocean acidification does not only change the pH of the ocean water. As a matter of fact, it also changes the gaseous concentration in the ocean, and to be particular, it increases the concentration of carbon dioxide. This is because of the reactions between carbon dioxide and water molecules to form more carbonic acid. And when it rains on the water masses, the level of carbon concentration rises further and further instead of subsidizing as carbon dioxide is absorbed to form more carbonic acid. This may lead to suffocation and even death of marine creatures. Second, loss of aquatic life. The seawater supports life at its normal conditions. Nevertheless, when the pH level is lowered or raised, some organisms are affected. Some of the aquatic include various types of fish, mammals such as whales, sharks, and many more. As increase in acidity makes living cumbersome and almost impossible for some living beings, this leads to the disappearance or death of some organisms in the ecologic environment. Third, food shortage. Ocean acidification contributes to the large problem of food shortage in many ways. When fish die, humans depend on them for food and livelihood are hit by the socioeconomic problems. This process also contributes to acidic waters, which have a more devastating effect on agricultural production. Acidic water results in an increase in soil activity. Such a thing makes it impossible for cultivation and production of certain crops. This leads to low production and starvation. Fourth, food web interference. Ocean acidification leads to the death and disappearance of some plants in the sea. When some organisms become extinct, their dependents are also threatened because they have nothing to feed on. Fifth, impact on human health. Humans depend on water for various purposes. When the ocean water acidity gets higher, the consumers or the users of such water are living in a perilous situation. Diseases such as cancers can easily be transmitted to humans when they consume fish intoxicated with higher sulfur concentrations. Sixth, the impact on the reefs. As more carbon dioxide is absorbed into the oceans, it bonds to form carbonic acid. The acid then produces hydrogen ion and bicarbonate ion, and the hydrogen ion bonds with free carbonate ions in the ocean to form other bicarbonate products. The problem with this reaction is that marine organisms possessing shells, corals, crustaceans, mollusks, foraminiferas, and coralline algae need the carbonate ions to make calcium carbonate shells and skeletons. Thus, the more dissolved carbon dioxide in the ocean, the less free carbonate ions accessible for forming calcium carbonate shells, skeletons, etc. Seventh, impact on open ocean planktonic oceans ecosystems. It must be remembered that planktonic ecosystems in the oceans are open. That is, they are not definite. It varies from place to place and also from ocean to ocean. In fact, it is the phytoplankton that forms the basis of the marine ecosystems. The phytoplankton carries out photosynthesis and thus begins the chain of the marine ecosystems. So if somehow their photosynthesis faces a problem, the entire marine ecosystem suffers. The fact is that the more CO2 levels, the more is the problem faced by the plankton is carrying out their photosynthesis. Increased acidity of the seawater hampers various processes of the planktons, like nitrogen fixation and others as well. 8. Coastal ecosystems are affected. Not just the marine ecosystems, the coastal ecosystems are affected too by the acidification of the oceans. The coastal ecosystems contain a variety of plants that form a unique habitat. With the acidification of the ocean, it is natural that the coastal areas too develop acidity in their soil. With a little bit of acidity might help in the better growth of the plants too, much acidity could really be detrimental for their health. Once the habitat is affected, it is natural that the entire ecosystem would be affected too. This entire chain causes a major disbalance in the ecological systems. This acidification also decreases the productiveness of the organisms found in the coastal areas. Their death rates might increase too. This might then lead to extinction of a particular species. 9th, high latitude oceans are at risk. The oceans located in the higher latitudes are one of those that are highly productive. The Southern and the Arctic Oceans are in fact the most productive of all oceans, teeming with life. These are some of the most exploited oceans as well. Already, this hampers the ecosystem of these oceans. Adding on to that is the problem of acidification. As the problem of acidification increases, life in these oceans is affected as well. Their productivity as well as their lifespan decreases. It is an enormous problem. So what are some solutions to ocean acidification? First is strict and relevant regulations. Human actions are best guarded by the policies of the land. The best and first step towards the fight against ocean acidification can be commenced through the ratification of legislation that can ensure that the waste handling among other pollution risk activities is controlled. Such regulations would spread to the Fisheries Department to ensure that safety is maintained in food consumption. Second is civil education. Governments and international organizations can come up with some platforms where they educate or sensitize the common citizens on the risk posed by climate change and ocean acidification. Such initiatives can instill some self-triggered discipline that acts as a guidance or the quest for education would also be necessary because the tips given in the theoretical context will not only be pertinent in real context, but also in the understanding of the policies. 3. Consuming only the right fish. In any case, an increase in acidity would make fish consumption a risky affair. This is why the authorities would be tasked with the responsibility of ensuring that only the less harmless fish find their way into the market. This can be helpful in reducing the chances of having food poisoning and carbon gas circulation in the environment. 4. Reducing the consumption of carbon-oriented energy sources. The presence of a high concentration of carbon in the atmosphere can be attributed to various human activities, which can be controlled to some extent. Carbon emitted from fossil fuels can be reduced through the minimalization of the use of these fuels. Adopting the use of alternate renewable energy sources can be the best available option. Diversification of energy sources, such as the use of solar and wind as the alternative energy sources, can be significantly paid off. When there is reduction carbon dioxide concentration in the atmosphere, there will be a resultant change in the ocean. The other viable option that can be reliable is geothermal, which is environmentally friendly. Geothermal power can be such an initiative because it comes with less emission of carbon dioxide in the atmosphere. This would reduce the chances of contaminating the ocean waters. 5th, use of alternative water sources. Because of the need to ensure that there is safety, skepticism may pay off. Such can be through the use of alternate water sources, such as the use of boreholes, wells, or tapped rainwater instead of ocean water domestically. This can help in minimizing possible ocean water pollution. 6. Eating less meat. This is not surprising at all. Raising livestock is a major source of greenhouse gases. It is these greenhouse gases that cause all the problems. By reducing our meat consumption, we would reduce the demand for meat. This, in turn, would result in lesser rearing and raising of livestock. As a result of the same, we would be effectively reducing the amount of greenhouse gases being released into the atmosphere. Although this might quite sound absurd at first, this is one of the most effective ways in which we can reduce the problem of ocean acidification. Next, what happens if the ocean acidifies? Ocean acidification reduces the amount of carbonate, a key building block in seawater. This makes it more difficult for marine organisms such as coral and some plankton to form their shells and skeletons existing, and they may begin to dissolve. How does ocean acidification affect sea life? The more acidic the ocean, the faster the shells dissolve. Animals that produce calcium carbonate structures have to spend extra energy either repairing their damaged shells or thickening them to survive. Using energy for this could impact the animal's abilities to grow and reproduce. How does ocean acidification affect us? Ocean acidification will affect humans too. It will affect the food we eat since most of our shellfish requires calcium carbonate to form or to fortify their shells. Many of the fish we eat are also dependent on shelled animals for their food source, so the entire food chain is in jeopardy. Another question is, what are some examples of ocean acidification? For example, sea urchin and oyster larvae will not develop properly when acidity is increased. In another example, fish larvae lose their ability to smell and avoid predators. The vulnerability of larvae may mean that while organisms may be able to reproduce, their offspring may not reach adulthood. What will happen if we don't stop ocean acidification? The impacts of ocean acidification could be enormous. The change in ocean chemistry leads to collapsing food webs, corrosive polar seas, dying coral reefs, and mass extinctions, which could alter our food, water, and air forever. Next, we're going to watch a few videos about this that kind of go a little bit more deep and in depth about what ocean acidification is, how it affects us, other things that are related to it.
Twin you might not have heard of, ocean acidification. Today's rates of ocean acidification resulting from human activities have major consequences for marine life, coastal communities, and the amount of CO2 in our atmosphere. To start, let's take a little trip back to high school chemistry class. Remember the pH scale? It measures the acidity of a substance on a scale of 0 to 14. The lower the number, the more acidic. The higher the number, the more basic or alkaline. Generally, ocean water is a little alkaline, but our present-day oceans are getting more acidic. This isn't a phenomenon that humans can feel or see, but it's literally changing the chemistry of the ocean, and animals are not used to that. Here's how it works. The ocean is kind of like a sponge. It absorbs nearly 30% of carbon dioxide in the atmosphere. This is the ocean doing us a big favor, especially as the concentration of CO2 is the highest it's been in 800,000 years. When carbon dioxide is absorbed by the ocean, a chain of chemical reactions takes place. One result of these chemical reactions is that carbonate ions become less available in the ocean. And here's why that matters. The most direct effect of ocean acidification is on marine calcifiers. These are organisms like oysters, mussels, shellfish, and coral. Marine calcifiers use carbonate ions to build strong shells, skeletons, and hard parts. Emily Osborne, a scientist who studies ocean acidification, told me a little more.
It's reducing what I like to refer to as building blocks that marine calcifiers or things that grow shells can use to build their shells.
As the ocean becomes more acidic, fewer carbonate ions are available, making the shells of these animals weak, brittle, and deformed. Ocean acidification also has indirect effects on marine life.
Larval or early life stages of fish can be particularly vulnerable to ocean acidification, so they don't grow as quickly or grow as large. They normally would under higher pH conditions. We also see that the olfactory system in fish, which is essentially like their ability to smell, can be impacted in some species, so they're not able to find food or avoid predators as effectively as they can.
Ocean acidification is an emerging problem that's already impacting the seafood industry. Animals like oysters are struggling to build their shells and survive because their habitats are becoming corrosive. Chefs and seafood purveyors are particularly concerned because of acidification's effects on the marine food chain.
Anyone who works in a shellfish industry is very familiar with ocean acidification, the impacts that it has on their business. They change their business practices and the way that they grow their organisms because of ocean acidification.
Scientists say small organisms at the bottom of the food chain, called pteropods, are the power bars of the sea, but pteropods are also struggling to survive as a result of an increasingly acidic ocean. According to the National Oceanic and Atmospheric Administration, the pH of surface ocean water has dropped by 0.1 unit since the Industrial Revolution. That might not sound like a lot, but the pH scale is logarithmic, not linear, so that 0.1 drop equates to a 30% increase in acidity. Just like atmospheric carbon dioxide has fluctuated in the Earth's past, so has ocean acidification. But the fluctuations in the past have taken place over long periods of time, allowing marine life to adapt. As today's rates of emissions continue to increase, scientists project that by the end of this century, surface ocean waters could be 150% more acidic since the Industrial Revolution. Scientists have begun to differentiate ocean acidification from coastal acidification, because the latter is also affected by other variables like agricultural runoff. Osborne conducted a study published in December 2019, which concluded that California coastal waters are acidifying twice as fast as the global ocean average. To come to this conclusion, Osborne and her team studied a fossil record containing 100 years worth of shells of a marine calcifier called planktonic foraminifera.
So I was looking at a sediment core, which essentially was like going through pages of a book layer by layer down the sediment core and looking at these fossil shells. And what the fossil shells were showing me was that they were literally thinning as a result of ocean acidification. So they were 20% thinner in the year 2000 relative to the ones that I found in the year 1900.
The period Osborne studied is important because it represents a time that humans became more dependent on carbon and emitted more carbon dioxide into the atmosphere.
The study that I conducted in the California ecosystem suggests that the pH over just a 100-year period during my study had declined 0.22 units, so more than twice as much in a shorter period of time.
Osborne and her team noticed some variability as a result of a naturally occurring phenomenon called coastal upwelling, which is when ocean currents bring colder, more acidic water from deeper in the ocean to the surface.
Coastal upwelling is a process that makes the California current ecosystem an extraordinarily vibrant and diverse ecosystem. It brings a lot of nutrients to the surface ocean, and we have vast fisheries because of that process. But at the same time, those nutrient-rich waters that are upwelled along the coast also have a lot of CO2 in them as well. And so in this part of the world, we have a bottom-up stress from upwelling, which the system is acclimated to. It's normal. These organisms are used to this variability. But we also have this long-term stress that's coming from the top down, from the atmosphere, that's imprinting on that variability.
So, in short, human activity is making the world's oceans more acidic, which is then exacerbated by natural phenomena like coastal upwelling. The coasts along the east side of both the Pacific and Atlantic Oceans also experience coastal upwelling, making them vibrant with life and nutrients, but also victim to this double whammy effect. Like the other effects of climate change we see every day, stopping acidification requires reducing our reliance on fossil fuels and cutting back on carbon emissions. The NOAA released a plan for how it will study ocean acidification over the next decade. It includes predicting changes in the ocean and how those changes will impact marine ecosystems. Ultimately, the NOAA hopes its research will help communities and economies that are affected by ocean acidification.
This is why I stopped using laundry pods. They waste water and pollute the environment with microplastics. Plastic jugs of laundry detergent are even worse.
With nearly 90% water, these clunky jugs are a waste of plastic and space. Over 700 million of these end up in landfills.
In Antarctica, few animals can survive the howling winds and frigid temperatures up on the land blanketed by snow. But here in the Southern Ocean, under the serene, cool blue ice cover, Antarctica is teeming with life. In these frigid waters live creatures that would feel right at home in a 1950s monster movie. Giant sea spiders, jellyfish, anemones, and sea urchins.
They're living in water that's so cold that you can't even put your hand in it for 5 seconds without feeling extraordinary pain. It's just like right above the freezing point of seawater. It's so cold.
Today, the ability of these animals to survive in sub-freezing waters is being tested by a new threat, ocean acidification.
The Antarctic and the Arctic are thought to be possibly some of the more vulnerable marine ecosystems to climate change. And they might be the first in time to really have acidic waters meet the organisms that live there.
What's making the oceans more acidic? Scientists blame the carbon dioxide created by the burning of fossil fuels. The CO2 goes into the atmosphere, but as much as 30% is then absorbed by the oceans. The more carbon dioxide, the higher the acidity.
Initially, scientists welcomed this absorption of carbon dioxide by the oceans because they believed it would reduce CO2 concentrations in the atmosphere. But as the oceans take in carbon dioxide, now the question for scientists is how much is too much?
We knew that we were burning things to make energy, and that carbon dioxide, some of it was ending up in the oceans. And for many people, that was seen as a good thing. What we're recognizing is that there are changes in the composition in the oceans.
In the last 150 years, as CO2 has increased in the atmosphere, the pH of ocean surface waters has dropped by around 0.1 pH unit. That's a 26% increase in ocean acidity. And the Intergovernmental Panel on Climate Change predicts an additional drop of 0.2 to 0.3 pH units by the end of the century. That's a 100 to 150% increase in ocean acidity since before the Industrial Revolution. As the ocean becomes more acidic, it makes it harder for marine animals that build their shells out of calcium carbonate, like corals and oysters. At the University of California, Santa Barbara, scientists are studying the effects of higher CO2 on sea urchins.
We mix the carbon dioxide into our seawater tanks to mimic future high CO2 oceans, levels that we thought we'd go to in 100 years or something. And we do start to see effects at those high numbers in terms of slowing down their growth. They are a little bit smaller at any time in development. And also there's some effects on fertilization, we think, when water gets really acidic.
Not far off the coast of UC Santa Barbara, ocean acidification could have a direct impact on people who make their living harvesting sea urchins.
My name's Bruce Steele. I'm a commercial sea urchin diver. I work at the Channel Islands, which are right here off the coast.
The boom for sea urchin sushi started with the Japanese back in the 1980s. Now the uni crop brings the state of California over $100 million a year and provides essential jobs to hundreds of divers and processors. But the changes to ocean chemistry have them worried.
The problems that we're seeing with animals like sea urchins or oysters are kind of a harbinger of problems that might be going on in the open ocean.
Two recent events clearly show that ocean acidification has already arrived on western shores and could have a direct impact on the seafood we eat. In 2007, Science magazine reported that surface water in places along the California coast was already more acidic than researchers predicted. Around the same time, news reports started trickling in from oyster hatcheries in Oregon and Washington state. Millions of larvae were dying. The culprit, ocean acidification.
It seemed that it was actually the change in the chemistry of the seawater that was killing the larvae.
The massive die-off alarmed both the seafood industry and scientists. In California, they joined forces to do something about it. They're sharing data and standardizing water measurements to determine which species are most vulnerable.
There's a crew of us, the oystermen, the fishermen themselves, scientists and other people in the community are getting together and kind of asking, how can we work together to address some of these growing economic issues.
Back in Antarctica, where scientists predict acidic conditions will be felt first, the options for Gretchen Hoffman's sea urchins are quickly dwindling.
It's kind of like a double-edged sword. They've learned to live in a really cold environment that stays cold all the time, and then here comes climate change. So the ocean's going to warm and the pH is going to change. And where are you going to go? Where can you migrate to that's colder if you're an Antarctic urchin? Well, nowhere, actually.
Since the beginning of planet Earth, animals have adapted to changing conditions. But adaptation can take thousands, even hundreds of thousands of years. Now, with millions of tons of carbon dioxide going into the oceans every day, can the creatures of the sea change quickly enough to survive in the changing oceans?
We have an incredibly productive ocean. When we go out there and do our research, when I'm waiting for the instrument to come up, I can see salmon jumping, that's amazing.
This issue of ocean acidification, it threatens that ability to rely commercially on these resources and also to rely on them recreationally and socially and culturally.
About 25 to 30% of the CO2 that's released from fossil fuel combustion ends up in the ocean. That lowers pH, and it also changes something we call saturation state, which is the corrosivity of that water.
Based on the chemistry of the water and how marine life respond to chemistry, the kinds of organisms that we think are the most vulnerable are the ones that build a shell. So oyster shells, clam shells, and corals.
I think the things that are most important to the public to understand is that what this issue is threatening is some of our food supply. There are people's livelihoods and generations of watermen who rely on producing oysters and other shellfish. So when we talk about ocean acidification, what we're talking about is a change in carbonate chemistry of the ocean due to the increase in atmospheric CO2 from fossil fuel combustion, as well as other local processes that change that chemistry. And so the issue comes in is that we're changing that chemistry faster than we have in the last million years in the Earth's history. And that's having predictable consequences on the chemistry as well as consequences on the organisms that we're just starting to understand now.
So we've identified the Oregon coast as one of these early impact systems. So our chemistry is already changing and has changed dramatically.
The waters that reach Oregon's coast, if you stand on the coast and look out and see this great blue expanse, you think, oh, that's just one big bathtub of water. You're not quite sure what's there, where it's coming from. But over the years, we understand very well how that water gets there. And that water reaches Oregon's shore from far across the North Pacific, off to the northeast of Japan, actually. When it's at the atmosphere, it gets the oxygen and the CO2 from the atmosphere mixed into it. It's cold enough there that the water gets dense or heavy and it sinks down to beneath the waves to about a couple hundred meters and starts this long journey across the North Pacific. And there are actually two branches. One of them comes across the northern Gulf of Alaska. Another one takes this amazingly convoluted route. Along that path, the oxygen gets lower, the CO2 goes up, the pH goes down, it gets more acidic before it reaches Oregon shores. So if you think about the rising CO2 levels in the atmosphere, the water we're seeing at depth off Oregon has the signature of many decades ago.
Even if we absolutely stop the CO2 emissions today and cap the atmospheric levels, there's still a 30 to 50 year increase we're going to see before that carbon, at least along our coast, works its way out.
The effects that we're seeing, the changes that we're seeing in the chemistry of the ocean that affects everything there. All living things and non-living things also are changing it in ways that are going to adversely affect the things that people care about, because it's affecting the creatures that live there and their habitat.
The oyster industry in the Pacific Northwest has already seen significant losses in production in oyster hatcheries. And so what it's meant to the oyster industry is approximated about $110 million in production losses. OSU has really sort of been a leader on this topic, and it's a bit out of necessity. And so the oyster industry really contacted Burke Hales and myself to understand what was happening in these oyster hatcheries and try to explore what's driving these problems. And so because of this upwelling system starts with CO2 levels that are higher to begin with and puts us closer to those thresholds for the organisms, they've had to deal with these problems kind of right off the bat. And so we've had this really productive industry academic partnership that has allowed us both to sort of provide information and applied research to let the industry increase production and deal with some of those losses in different mitigation adaptation strategies, but also do some really good fundamental basic research on understanding those responses.
At Whiskey Creek in about 2007, suddenly the hatchery where they produce the tiny larval oyster that are sold to the growers that actually produce the commercial product, the hatchery was unable to produce those, could not meet their demand, and effectively they were producing no commercially viable larvae.
When we first saw this problem, of course, we'd never seen anything like this there before, where you lose all the larvae in the hatchery on a given day. We saw some die-offs that we'd never seen before, and it really scared us.
What we found is that what almost entirely determined the success of a hatch, of a spawn, was the carbonate ion, or the shell mineral stability, in the water in which they were spawned. And so it was a very narrow window of time. The first 48 hours of the life of these organisms seemed to entirely predict how they would do 2 weeks later.
What's happened here is basically we have to deal with ocean acidification. It's just, and it's not to say that all the water we pump in is bad. It's just that when conditions are right, you get upwelling and whatnot, then you bring up this low pH water, and you're bringing up water that basically larvae don't like. And it's very difficult, if not impossible, to grow in that type of water without somehow altering the water as it gets into the tanks. Just because we've done a few of these things, by no means, I think we're just scratching on the surface of this problem. And I think, at least in my lifetime, that we'll still be trying to figure it out, and probably long after I'm dead. I think it's going to be something that people are going to struggle with and try to make better.
One other canary in the coal mine is a pteropod. These are very delicate, beautiful, elaborate swimming snails. They are important in their own right as members of zooplankton communities, but they are also a very highly prized food for salmon.
There's some really good work being done now that shows pteropod effects in the environments now without experimental manipulation, that we're seeing the shells of the pteropods actually partially dissolved.
Ocean acidification may actually disrupt the ability of some of these microorganisms to assimilate nutrients. We're beginning to pick up some of those more subtle impacts, and it's scary.
The impacts of having these kinds of changes happen on such a large scale, and in the event that they became catastrophic, are really more than just economic. Clearly it affects my ability to do business here, to sell local fish if the supply is diminished or threatened in that way. And of course, everybody else who's involved in that, the entire fleet that goes and catches, the support services here, the supply stores, the ice purveyors, the transportation providers. But it really impacts you on another level, because for somebody like myself that considers themselves a third-generation commercial fisher, even though I don't go out and ply the waters every day anymore, it's really your whole, kind of your legacy and culture. There's a whole identity for us here on the coast that are in this industry that we have a lot of pride in, and it's something that would be impossible to replace.
We haven't seen thinner shells in crabs yet, but I believe that we better watch for them, you know. If 9 out of 10 scientists of pretty good reputation are all telling us the same thing, why is it so hard for us not to believe them, or at least give it a shot? You know, what if we're wrong? What if we're wrong and we don't react appropriately? Things are going to change big time. We have an obligation, I think, to do what we can do to understand and mitigate damages and correct trends that are negative. You know, our existence might rely on this. We don't know.
We know that these impacts are happening. What we don't know, and what we need to know, is what's happening to the ecosystem at large. We anticipate and are concerned about impacts to fish. We're concerned about impacts to crustaceans like crab and shrimp, but we need more research. And what we know now is that some of the species that are low on the food chain are being impacted, and that implies that there are ecosystem-wide, food web-wide impacts that we're going to start to see.
We're going to see changes in chemistry that the rest of the ocean won't see for decades and decades. So on the one hand, we're going to be the hardest and first hit. But on the other hand, I think it's important that what we learn today in Oregon's coastal waters, that is invaluable. There's really no substitute for the kinds of information that we're going to gain by understanding our ocean. There's no substitute for that.
For most of the year, the Gulf of Mexico is teeming with marine life, from tiny crustaceans to massive baleen whales. But every summer, disaster strikes. Around May, animals begin to flee the area. Soon, creatures that can't swim fast enough begin to suffocate and die off in massive numbers. From late spring to early autumn, thousands of square kilometers along the coast become a marine dead zone, unable to support most forms of aquatic life. This strange annual curse isn't unique. Dead zones like this one are formed all over the world, but to explore what's creating these lethal conditions, we first need to understand how a healthy marine ecosystem functions. In any body of water that receives sufficient sunlight, plant-like organisms such as algae and cyanobacteria thrive. Clouds of algae streak the surface of deep waters, and in shallower regions, large seaweeds and seagrass cover the ground. Not only do these organisms form the foundation of local food chains, their photosynthesis provides the oxygen necessary for aquatic animals to survive. Besides sunlight and CO2, algae also depends on nutrients like phosphorus and nitrogen. While such resources are typically in short supply, sometimes a surrounding watershed can flood coastal waters with these nutrients. For example, a large rainstorm might wash nutrient-rich sediment from a forest to a lake. These additional resources lead to a massive increase in algae, known as eutrophication. But rather than providing more food and oxygen, this surge
just doing my videos.
deadly consequences.
Doing my videos.
The more algae grows on the surface, it
Really good. I think I'll have a third one tonight.
die off,
Thank you.
in a process which uses up the water's already depleted oxygen supply. Over time, this can reduce the oxygen content to less than 2 milligrams of oxygen per litre, creating an uninhabitable dead zone. There are rare bodies of water that rely on natural eutrophication. Regions like the Bay of Bengal are full of bottom-dwelling marine life that has adapted to low oxygen conditions. But human activity has made eutrophication regular and widespread occurrence. Nutrient-rich waste from our sewage systems and industrial processes often end up in lakes, estuaries, and coastal waters. The Gulf of Mexico is one of the largest dumping zones on Earth for one particular pollutant, fertilizer. American agriculture relies heavily on nitrogen and phosphate-based fertilizers. 31 states, including America's top agricultural producers, are connected to the Mississippi River Basin, and all of their runoff drains into the Gulf of Mexico. Farmers apply most of this fertilizer during the spring planting season, so the nutrient flood occurs shortly after. In the Gulf, decomposing algae sinks into the band of cold salt water near the seafloor. Since these dense lower waters don't mix with the warmer fresh water above, it can take 4 months for tropical storms to fully circulate oxygenated water back into the Gulf. This dead zone currently costs U.S. seafood and tourism industries as much as $82 million a year, and that cost will only increase as the dead zone gets bigger. On average, the Gulf dead zone is roughly 15,000 square kilometers, but in 2019 it grew to over 22,000 square kilometers, approximately the size of New Jersey. Human activity is similarly responsible for growing dead zones around the world. So what can be done? In the short term, countries can set tighter regulations on industrial runoff and ban the dumping of untreated sewage into ocean waters. On farms, we can plant buffer zones composed of trees and shrubs to absorb runoff. However, long-term solutions will require radical changes to the way we grow food. Farmers are currently incentivized to use techniques that reduce the health of the soil and rely heavily on nitrogen-rich fertilizers. But there will be less need for these chemicals if we restore the soil's natural nutrients by planting diverse crops that manage soil erosion and fertility. Hopefully, we can make these fundamental changes soon, because if we don't, the future of our marine ecosystems may be dead. Fish larvae. By 2050, there will be more plastic and trash in the ocean than fish. Could we find out more about this serious threat on Earth.
Okay, I know that was a lot of videos, but I hope that that explained a lot of like more detailed information. But we're gonna get back to some questions and some answers, things like that. The world's oceans could virtually be emptied by fish by 2048. A study shows that if nothing changes, we'll run out of seafood also by 2048. If we want to preserve the ecosystems of the sea, change is needed. What animals are affected by ocean acidification? Shell-forming animals like corals, crabs, oyster, and urchins are getting hit first because ocean acidification robs seawater of the compounds that these creatures need to build shells and skeletons, impairing their development and ultimately their survival. How does ocean acidification affect climate change? If acidification decreases marine emissions of sulfur, it could cause an increase in the amount of solar energy reaching the Earth's surface, speeding up warming, which is exactly what the Nature Climate Change Study predicts. It's one more surprise that the oceans have in store for us. Where are the effects of ocean acidification hitting the hardest? So, the effects of ocean acidification are hitting the hardest in Japan. Japan ranks as the most vulnerable nation to the impacts of ocean acidification out of the 187 nations considered. How does acidification affect water quality? Ocean acidification is degrading seawater quality with adverse impacts on marine ecosystems. The primary known consequence of ocean acidification is that it impairs the ability of marine animals to build and maintain their protective shells and skeletons. Where does the ocean acidification occur the most? Like which oceans? So we just talked about what nation it hits the hardest, so what oceans does it hit the hardest? So the polar oceans in the Arctic and Antarctic are particularly sensitive to ocean acidification. How can we prevent ocean acidification? So the most effective way to limit ocean acidification is to act on climate change, implementing solutions to dramatically reduce the use of fossil fuels. If we dramatically cut our global warming emissions and we limit future warming, we can significantly reduce the harm to marine ecosystems. Next question is, what will happen to the ocean by 2050? Experts say that by 2050 there may be more plastic in the fish than fish in the sea, or perhaps only plastic left. Others say that 90% of our coral reefs will be dead, waves of mass marine extinction may be unleashed, and our seas may be left overheated, acidified, and lacking oxygen. It is easy to forget that 2050 is not that far off. That is also less than 30 years away, which is terrifying because I'm just turned 18. I hopefully won't be gone by the next 30 years. So that's very scary. So we need to act now. It's actually terrifying. There's so many people in the world that know about this issue and how it's not getting resolved. How does ocean acidification affect the economy? So economists say they predict that unchecked acidification could decrease shellfish harvests and increase consumer prices. They're taking a halt ocean and coastal acidification. A falling supply of shellfish is estimated to lead to consumer losses of roughly $480 million per year by the end of the century. Next is how does ocean acidification affect greenhouse gases? The ocean plays an important role in regulating the amount of carbon dioxide in the atmosphere. As atmospheric concentrations of carbon dioxide rise, the ocean absorbs more carbon dioxide. Does plastic contribute to ocean acidification? New research has found that pollution from plastic waste dumped into the world's ocean is correlated with ocean acidification, which occurs when the water's chemistry is altered as CO2 is absorbed by seawater. Next question that's also very important for us is, can you reverse ocean acidification? So once the ocean is severely affected by high carbon dioxide, it is virtually impossible to undo these alterations on a human generation timescale, said Sabine Mathias of the Potsdam Institute for Climate Impact Research in Potsdam, Germany. And my last question for this video, our second to last question, is how long has ocean acidification been happening? Ocean acidification is now thought to occur faster than it has been in the last 20 million years. In the past, similar changes in pH have happened naturally, but over much longer periods of time. And my last question, before I show you a chart, and that's it, what does ocean acidification affect human and fishes? So ocean acidification can modify the abundance and chemical composition of harmful algae blooms in such a way that shellfish toxicity increases and therefore human health is negatively affected. So I'm going to show some diagrams really quickly and explain them of what the process actually looks like of ocean acidification. Hopefully that also can clear things up. I'm sure the videos did a really good job. This is just a last clarifying little picture diagram. Yeah. So this is the scientific scale of what it looks like, ocean acidification looks like. The pH scale, you can see what it looks like. And yeah, you can see now what it looks like in the late 1800s and the projected acidity also of the seawater. You can see that it keeps getting more and more acidic than alkaline. So yeah, a lot of fewer and smaller marine calcifiers now is what's being predicted, instead of abundant healthy corals, mollusks, and other marine calcifiers. And this is just one more that kind of explains it in a smaller way. If you like chemistry, this is definitely for you. You definitely know what all this means. But yeah, oceans absorb carbon dioxide from the atmosphere, creating carbonic acids in the water. So this is all for my video today. I hope that you continue watching and that you are interested in this. I'm super interested in this, and I hope that you can reach out and make a change because we need it so badly. And a lot of the solutions that we have is just spreading the news, because believe it or not, not all people know about this. I had no idea what ocean acidification was and that it was really harming our ecosystem. I just didn't know, and I'm sure that if I didn't know, there's so many more people that also were unaware. It's not something that I've ever been taught in school, which is pretty unfortunate. I feel like this definitely needs to be talked about way more, because it's not common sense. You don't commonly know the issues going around the world unless you experience it firsthand. And I live right on the ocean, and I still had no idea about what ocean acidification was. So yeah, I definitely think that just doing research, and I think this video was so information packed with videos and diagrams and all these facts. So yeah, I definitely stick around for my last 3 videos. We have 3 down, 3 to go. So yeah, I definitely stick around and watch my videos, and yeah, we have some interesting ones coming up. But thank you so much for watching. I hope that you come back for my next 3 videos that are going to be super fun to talk about. In my last 3 videos, we'll be talking about biodiversity in the ocean, so more just all the animals and things like that, and where they live. It'll be more a fun, kid-friendly one. And then the next one will be about policy change to control ocean dumping. And the last one will be plastic ocean pollution. So yeah, definitely stick around. Thank you so much for watching. I hope you have a great day, and make sure to like and subscribe. Bye!